Okay, students, then we'll continue that AM receiver, which is, what is the receiver we are doing is super heterodyne receiver, right? Okay. Now see here, now we are at here. A tuned circuit is used at the input of the mixer to suppress the image frequency, to completely avoid the image frequency, so that image frequency signal strength should be as minimum as possible, such the image rejection ratio should be as high as possible. Okay, so this tuned circuit and a frequency response of this tuned circuit is like this. Gain at FSI should be as minimum as possible. Okay, so practically here I just write 3 points. Practically the image rejection ratio should be as high as possible. Now the image like a signal to noise ratio, for example, for better understanding you take the signal to noise ratio. When the signal to noise ratio is as high as possible, effect of noise is as less as possible. Similarly, image rejection ratio should be as high as possible, then the signal strength is very less at FSI. So noise signal strength should be very less, so signal to noise ratio should be very high. Okay, and to improve the image rejection ratio, tuned circuits are connected in cascade. Okay, so if you cascade the tuned circuits, the overall image rejection ratio is increased. When the image rejection ratio is increased, and obviously image frequency should be decreased, as image frequency signal strength is decreased and image rejection ratio is very high. So the tuned circuits are connected. This is the first tuned circuit and a second tuned circuit, and the tuned circuits are connected in cascade. Then this image rejection ratio is alpha 1, this is alpha 2. So overall image rejection ratio is alpha 1 into alpha 2. Suppose here this quality factor is Q1, this quality factor is, if this tuned circuit quality factor is Q1, if this tuned circuit quality factor is Q2, now in such a situation, alpha, which is equal to alpha 1 into alpha 2, which is equal to square root of 1 plus Q1 square into rho square into 1 plus Q2 square into rho square, right? Now if Q1 is equal to Q2, if this is separately Q1 and Q2 is available, if Q1 which is equal to Q2, now these two tuned circuit quality factors are same, then alpha, which is equal to alpha 1 into alpha 2, which is square root of 1 plus Q square rho square into square root of 1 plus Q square rho square, which is equal to square root cancel 1 plus Q square into rho square, 1 plus Q square into rho square. Now this is image rejection ratio. So a tuned circuit is used at the input of the mixer, and at the same time a tuned circuit is used at the RF amplifier, which is also used to improve the image rejection ratio, which means that a tuned circuit is used here. Now this is the tuned circuit. Let us assume here this is alpha 1, this is alpha 2. So overall image rejection ratio is alpha 1 into alpha 2. Now in super heterodyne receiver, a number of total tuned circuits are, one is at IF amplifier, which will act as a band pass filter. Now the IF amplifier is having a tuned circuit, act as a, this tuned circuit acts as BPF, band pass filter, right? And this is tuned circuit at the mixer stage to avoid a image frequency, to suppress the image frequency, and this tuned circuit at RF amplifier further improve the image rejection ratio. I will tell you with one example problem also. Okay, and one more thing, but this tuned circuit will act as a band pass filter, and this band pass filter characteristics are fixed. This band pass filter characteristics are fixed, and a bandwidth of this tuned circuit, the bandwidth of this tuned circuit is resonant frequency by quality factor. This resonant frequency is always fixed. The intermediate frequency is 455 kHz. Quality factor is 45.5, such that why quality factor is only 45.5? Then only the bandwidth, which is equal to 10 kHz. The each AM tuned station bandwidth everywhere will be 10 kHz. Okay. Now this is the total super heterodyne receiver. Now this is IF stage, then IF amplifier increasing the IF signal strength. Demodulator is IF to AF. Demodulator will get back the IF to AF. AF amplifier to increase the audio quality signal strength. Power amplifier is impedance matching. Both are also try to improve the signal strength, and you can get a good quality of the audio signal. Okay, this is the total super heterodyne receiver. Okay, note down. To overcome selectivity problem, what we are faced in TRF receiver, to overcome selectivity problem, RF is go to intermediate stage, IF, then go for AF stage. Previously no IF stage in TRF receiver. RF is directly go to AF. RF is directly go to AF, whereas in TRF receiver. But what is the problem we are facing in TRF receiver? Facing selectivity problem in TRF receiver, where RF is directly go to AF. So there is a tune circuit problem. So to avoid that selectivity problem, now RF is having an intermediate stage of IF, and to avoid that selectivity problem. Okay, no doubt. Now this is the local oscillator. EFL, down conversion is greater than this is. Clear or not? And this IF is constant, and it is depends upon application. Which is 455 kilohertz in AM radio. So which is always fixed as 455 kilohertz. So the local oscillator frequency is adjusted. Now what is that local oscillator? Now this is the local oscillator. This local oscillator is nothing but an LC tuned circuit. Now practically the local oscillator is a Hartley oscillator. Now for example, this local oscillator frequency is FL, which is equal to 1 by 2 pi root LC. Now this capacitor is changed and this local oscillator frequency is adjusted. So when this local oscillator frequency is adjusted to down converted, so the local oscillator frequency is adjusted to down converted to IF, which is 455 kilohertz is always. The local oscillator frequency FL is adjusted to down conversion of FL minus FS, which is equal to IF, which is equal to 455 kilohertz. This process is called as tuning. The process of selecting the required signal is called as tuning. Okay, this process of local oscillator is adjusting is called as tuning, and it is always down converted to 455 kilohertz and low resonant frequency is 455 kilohertz. Quality factor is 45.5. Then only the bandwidth of the tuned circuit is 10 kilohertz. Fixed. This one is fixed. Okay, note down. Clear or not? Now we'll solve classroom workbook problems. Classroom workbook question number 1. Okay. Now what is the question number 1 is a super heterodyne receiver. Listen carefully. A super heterodyne receiver having no RF amplifier. A super heterodyne receiver having no RF amplifier means this is not there. This tuned circuit is not there. Okay. A super heterodyne receiver having no RF amplifier means there is no circuit. This is tuned to 555 kilohertz. Is tuned to 555 kilohertz. Means Fs is 555 kilohertz. Is tuned to 555 kilohertz, and the local oscillator frequency is adjusted to, here local oscillator frequency is also given, not required but given. Local oscillator frequency is adjusted to 1010 kilohertz and quality factor of the tuned circuit is 50. Quality factor of the tuned circuit is 50. Determine intermediate frequency, image frequency, image reaction ratio. Now, what is intermediate frequency? Intermediate frequency is FL minus FS, which is equal to 1010 kilo minus 555 kilo, which is equal to 455 kilohertz is the intermediate frequency. Next, image frequency. Image frequency FSI, which is equal to FS plus 2 into IF, which is equal to, what is Fs? Fs is 555 kilo plus 2 into, what is IF? IF is 455 kilo. Now, which is equal to 555 kilo plus 455 kilo. This is 910 plus 1465. Yes, this is 1465 kilohertz is the image frequency. And what he is asking, image reaction ratio. He is also asking image reaction ratio. So image reaction ratio, if you want to find, first you find rho FSI by Fs minus Fs by Fsi, which is equal to, Fsi is available, Fs is available. If you calculate, now that is 2.2608. and image reaction ratio, now this is image rejection ratio alpha, which is equal to square root of 1 plus q square into rho square, which is equal to square root of 1 plus q. Q is 50 square into rho is 2.2608 whole square, and the image reaction ratio, which we are getting as 113. 113 means what? Now image frequency signal strength. Now what is the meaning of that? Image reaction ratio is 113, which means image frequency signal strength. Image frequency signal strength is suppressed by a factor of, image frequency is suppressed by a factor of 1. This much of factor, the image frequency is suppressed, means image frequency signal strength, for example, is 1. Now that is further decreased by a factor of 113. Image frequency signal strength is suppressed by a factor of 113, right? Now this is the image reaction ratio meaning, no doubt. Or we write image frequency signal strength is reduced, is a good word, reduced by a factor of, okay, whatever it may be, that much is down by 113. Now, clear or not? Now that is question number 1, no doubt. Now, classroom workbook question number 2. Now, what is the question number 2? A super heterodyne receiver having RF amplifier is tuned to, now there is an RF amplifier, is tuned to 1200. A super heterodyne receiver having an RF amplifier is tuned to 1200 kilohertz. The intermediate frequency intermediate frequency is given. Intermediate frequency is 450. Actually, it is 455. Okay, in problem, okay. Not. The quality factor of the tuned circuit at the RF amplifier. The quality factor of the tuned circuit means here using tuned circuit. The quality factor of the tuned circuit at the RF amplifier and the quality factor of the tuned circuit at the RF amplifier and at the input of the mixer are same, which is equal to, this is quality factor of the tuned circuit Q1, this is quality factor of the tuned circuit at the input of the mixer is same and which is equal to 65. So which means that now the quality factor at the RF amplifier is Q1, quality factor at the input of the mixer is Q2, which is equal to 65. Therefore, the image reaction ratio which is equal to alpha 1 into alpha 2. Clear or not? Now this is alpha 1 into alpha 2 overall image reaction ratio. But what he is asking? He is asking determine the image frequency and image reaction ratio. Okay. So what is the image frequency? Now the image frequency is Fs plus 2 into Fs is 1200 kilo plus 2 into If is 450 kilo. 900 plus 1200 which is equal to 2100 kilohertz is FSI. Now the image reaction ratio FSI by Fs minus Fs by Fsi. Now this is the image reaction ratio which is 1.178 and image reaction ratio. Now see here image reaction ratio. Image rejection ratio which is alpha which is equal to alpha 1 into alpha 2 which is, what is alpha 1? Square root of 1 plus q1 square into rho square root of 1 plus q2 square into rho square. But what happened here? Q1 is equal to Q2 which is equal to, now square root cancel, which is equal to 1 plus q square rho square, because Q1 which is equal to Q2 which is equal to Q1 which is equal to Q2 which is equal to Q. Okay. Now which is 1 plus 65 square into rho square. Therefore, now the image rejection ratio is 5869. This is approximately 5869. See, then you understand or not? Now here the image rejection ratio previously is 113. Now the image rejection ratio is 5000, right? Approximately 5600 is nothing but 5870 means approximately 6000. So image frequency signal strength is, image rejection ratio is very, very high. Image rejection ratio is very, very high. Very, very high. So image frequency signal strength is reduced by a factor of 5869, means almost no FSI, no image frequency, be almost zero. 1 by 1000 time itself is 0.0. 1 by 6000 times, okay, 0.000 something is almost negligible, almost eliminated the image frequency. Why this image reaction ratio should be as high as possible? Because now here the tuned circuits are connected in cascade, two tuned circuits. See here, now this is advantage of the tuned circuit. I am writing one point. So if you use the tuned circuit at RF amplifier, further improve the image rejection ratio. If you connected a tuned circuit at the RF amplifier, image rejection ratio is increased and it is very, very high. Understand or not? Hold on. So this is the previous problem is first problem, no RF amplifier. Second problem, RF amplifier. If you use the RF amplifier and if you use the tuned circuit in the RF amplifier and this image rejection ratio is very high and the image signal strength should be suppressed and which is very, very less. Clear? Now this is question number 2. Now question number 3. Classroom workbook question number 3. A super heterodyne receiver having no RF amplifier is tuned to, means now this is not there. Means if this is not there, I may expect that the quality factor image rejection ratio is not this much, okay, is less. So a receiver, a super heterodyne receiver having no RF amplifier and is tuned to, having no RF amplifier and is tuned to 1000 kHz and is tuned to 1000 kHz and intermediate frequency is 455 kHz. Intermediate frequency is 455 kHz. Quality factor is 100 of the tuned circuit. Quality factor is 100 of the tuned circuit. Now determine, what he is asking is, he is asking to determine image frequency, image rejection ratio. Determine the image frequency FSI, which is equal to Fs plus 2 into If. FSI, which is equal to Fs plus 2 into If, which is equal to 1000 plus 455 into 2, 1910 kilohertz. Is it right or not? Yes, now this is 1910 kilohertz. Now what is rho? Rho, which is equal to Fsi by Fs minus Fs by Fsi, which is equal to, this is 1.386. Now the image rejection ratio. Now image rejection ratio, which is equal to square root of 1 plus q square rho square. Quality factor is 1000. now which is equal to 1 plus q square is 100 square into rho square square root of, now the image rejection ratio is image rejection ratio which is equal to 138.6. The image rejection ratio which is 138.6, right? Now this is the question number 3A, A bit. Now see here, see carefully, okay? Now what he is asking is, now B bit is, repeat all the above calculations if the receiver is tuned to, repeat all the above calculations if the receiver is tuned to 25 megahertz. So now Fs is increased to 25 megahertz, intermediate frequency and quality factor is same, quality factor is 100, okay? So now IF is 455, it is not changed, okay? So only asking repeat all the above calculations and if the receiver is tuned to 25 megahertz, therefore FSI which is equal to Fs plus 2 into IF, now which is nothing but 25.91 megahertz. This is 25.91 megahertz, and the rho which is equal to FSI by Fs minus Fs by FSI. Now this value which is 0.071, and image rejection ratio which is equal to square root of 1 plus q square rho square which is equal to square root of 1 plus q is 100 square into rho square. So image rejection ratio which is equal to 1.38, sorry, alpha which is equal to 7.2. So see these numerical values, okay? Observe these two problems, okay? Now question number 3. Now the receiver is tuned to 1000 kilohertz and these are the image rejection ratio, but the receiver is tuned to 25 megahertz. These are the values. So now what you want to identify here is, this is okay, image rejection ratio 138.6 is okay, good. But what happened the image rejection ratio? This is good, this is not good, is less, image frequency is not suppressed, image frequency signal strength is not suppressed, not reduced, because image rejection ratio is very less. So now what is our job? Our job is to improve. Now we try to improve image rejection ratio. How to improve the image rejection ratio? What are the modalities to, what are the techniques to improve the image rejection ratio? Now we will see, okay? Now you just see these two problems. Here image rejection ratio is very less. Now we will try to improve the image rejection ratio. What are the techniques is required to improve the image rejection ratio? Okay, now we'll see. Now see here, to improve image rejection ratio, what are the techniques available? We will see. To improve the image rejection ratio which is equal to square root of 1 plus q square rho square. If you want to increase, image rejection ratio should be increased. Now by increasing, image rejection ratio should be increased, quality factor is increased, or rho should be increased. If you want to improve the image rejection ratio, you should increase the quality factor or you should increase the image rejection ratio. So if you improve the image rejection ratio, there are two options for us. One is to improve the quality factor, another is improve the rho value. To increase the quality factor, image reaction ratio is increased, or to increase the rho value and image reaction ratio is increased. Now first we will see, now if we increase the quality factor, what happen? Okay, if we increase the quality factor, okay, note down this. Now case 1, I just concentrate. Case 1 is to increase quality factor. To increase quality factor, what happens? If quality factor is increased, what should be happening? I will explain clearly here, you just concentrate. Now this is the gain versus frequency characteristics of the tuned circuit. Okay. Now see here what happened. This is Fs, this is Fsi. Now this is gain at Fsi. Originally this is gain at Fsi. Clearly observe here, this is a original gain versus frequency characteristics. This is gain at Fs, and generally FSI is a high frequency. This is gain at FSI. Okay, originally. Now I am increasing the quality factor. What happened? Sir, why you are writing a characteristics here? Now I am increasing the quality factor. What happened? What is the bandwidth of the tuned circuit? The bandwidth of the tuned circuit is resonant frequency by quality factor. If I increase the quality factor, bandwidth is decreased. Okay, that's why I write here. When bandwidth is decreased, gain is increasing. Therefore, I am writing the characteristics like this. Now see here. So what happened? Now this is further increased. Again, bandwidth is decreased. Now what happened now? If bandwidth is decreases, now this is gain at FSI. Now see what is the effect? When quality factor increases, bandwidth is decreases. When bandwidth is decreases, now what is the fact? This is the first step. Now the second step is when bandwidth is decreases, gain at FSI is decreased. When gain at FSI is decreased, what is image reaction ratio? Gain at Fs to the gain at FSI. When this FSI is decreased, gain at FSI, image reaction ratio is increased. So what we want? We want to increase the image reaction ratio. To increase the image reaction ratio, quality factor is increased. When quality factor is increased, bandwidth is decreased. When bandwidth is decreasing, gain at FSI is decreases. When gain at FSI is decreases, image reaction ratio is increased. Now whatever we want, now that will be fulfilled when in order to increase the quality factor. Clear or not? Yes. Now the thing is to increase the quality factor. Listen now carefully. Practically quality factor increasing method is not at all preferable. Why? What is the reason behind that? Why the quality factor? Whatever you want, you achieve. Now gain at FSI is decreasing, image reaction ratio increasing. So, but why you are not using practically? Because when quality factor increases, now that effect is on, when quality factor increases, that effect is on bandwidth. Is it right or not? What happened to the bandwidth? Bandwidth is decreases when quality factor is increases. When bandwidth is decreases, no, is not acceptable, because not at all preferable practically, because it is affected the, because its effect, it is affected the bandwidth, it is affected the bandwidth. Each AM station bandwidth is, each AM station bandwidth is 10 kilohertz only. Each AM station bandwidth is only 10 kilohertz. Am I not? So practically quality factor is increasing, whether it is not all preferable, because it is affected the bandwidth. It is affected the bandwidth. Now each AM station bandwidth is 10 kilohertz. Okay, no doubt. So there is no other option. Then the other option, we have to go for rho increasing. But how? Rho is nothing but a constant. But how you increasing the value of rho, we will see. Go first you note on this. Okay. So this method is not at all accepting practically. So we never use quality factor increasing in order to improve the image reaction ratio. Therefore now there is a second method. The second method, which is nothing but increasing rho value. Increasing the rho value. Now this is rho value is increasing. Now how to increasing the rho value? So this is a constant, but how to increasing the rho value? Now see here. Now rho increasing means IF is increasing. What I am saying? Rho increasing, which means IF is increased. So how that is possible? When rho increasing, how the IF is increasing? So we will see with some examples such that you can easily understand. Okay. Now see here. Now what I am doing is, here image reaction ratio is very less. So to improve the image reaction ratio, now our aim is to improve the image reaction ratio, and here FS is 25 megahertz, IF is 455 kilohertz, quality factor is 100. Okay. So what I am saying is, when rho increasing means, which means IF is increased. Therefore now I am asking one question. Now this is the question. Determine same problem. Determine new value of IF such that image rejection ratio at 25 megahertz is 138.6. Okay. Determine the new value of IF. See here. What is the image rejection ratio here? 7.2. But what I am doing now, I am now here image rejection ratio is 7.2. Now I want to improve the image rejection ratio. Image rejection ratio should be improved to 138.6. So how it is improved? When you want to improve the image rejection ratio, then only the option is rho increases. But what I am saying is, rho increases is nothing but intermediate frequencies increases. So now I am asking question, determine the new value of IF such that image rejection ratio at same 25 megahertz is 138.6. But here is 7.2, but here is 138.6. Now alpha, which is equal to square root of, now see here, alpha which is equal to square root of 1 plus q square rho square, which is equal to 138.6. 138.6. Therefore, quality factor, I am not changing the quality factor clearly. See here, quality factor is how much? Same. Quality factor is 100. Here is also 100. What is the Fs? Fs is same. Fs is also not changed. Fs is at Fs equal to 25 megahertz. Now, what is Fs? Fs is 25 megahertz. Now, this is alpha. So, 1 plus q square rho square, which is equal to 138.6 whole square. So, 1 plus q is 100 square, which is equal to rho square, which is equal to 138.6 whole square. And what is the rho value? The rho value here is 1.386 you can get. But what I want, so what is rho? Rho, which is nothing but Fsi by Fs minus Fs by Fsi. Now here what I am doing here is, now Fsi can I write like this, Fs plus 2 into If by Fs minus Fs by what is Fsi? Fs plus 2 into If, which is equal to rho, which is already calculated, 1.386. What is Fs? Fs is also available. What is Fs? Fs is 25 megahertz. Fs is 25 m. Fs is 25 m. Fs is 25 m. Fs here is 25 m. Therefore, if you simplify, now this If value is how much? Now this is 11.4 megahertz. What I am saying is correct or not? Rho increases. Now first here, what is earlier rho? Rho is 0.071. Now what is rho? Rho is 1.386. Rho is increased. Now what happened? When rho increases, which means If is increased. What is If earlier? If is 455 kilohertz. If is 455 kilohertz, right? This is If. This is If. Now, what is If here? Now If is 11 megahertz, that is 455 kilohertz. This is 11 megahertz. Now If is increased. Therefore, increasing the rho value, now which means If is increased. But the question here is, sir, if If is increases, how the image reaction ratio is increased or not? So here previously If is 455 kilohertz. Now at this stage If is 455 kilohertz. Now image reaction ratio is only 7.2. But at this stage, here If is 455 kilohertz. At this stage 7.2. But here If is 11.4 megahertz. If is 11.4 megahertz and intermediate frequency is 11.4 megahertz and image reaction ratio is 138.6. Is increased or not? Yes. So when If is increased, image reaction ratio is increased. That is theoretically, but students are asking, sir, show me the practical way. So values, numerical values, as per the numerical values, okay, but we want to improve the image reaction ratio when intermediate frequency is increased. Okay, then that also I will show you practically. See here, see the graphs. Okay. Now before that, you write some points here. What is Fs here? Fs is 25 megahertz. What about here? Here is also 25 megahertz. What is the quality factor here? 100. What about the quality factor here? 100. Now this is Fs. This is Fs. Now see here. This is FSI. What is the difference between Fs and FSI is 2IF. Am I right now? Now the difference between Fs and FSI is 2IF because Fs minus FSI is nothing but 2IF. So now this IF is increased. Am I right now? Now see the student. When this IF is increased, means this separation is increased or not? This gap is increased or not? Yes. But quality factor is not changing, bandwidth is not changing. Okay, characteristics will be same. Now this gap is increased. So this is 2IF. So quality factor is same, Fs is same, but this separation is increasing, means IF is increasing. When IF is increasing, what happened? Now see here. Previously, this is gain at FSI. The gain at FSI here is some 10, let us assume. But now see here. Now this is gain at FSI. This is gain at FSI is 0.1. Decrease or not? Right? So now here image reaction ratio is gain at Fs to the gain at FSI is 1 by 0.1 is 10. But here image reaction ratio gain at Fs to the gain at FSI is 1 by 10, which is 0.1. This is not at all preferable. This is always preferable. Okay. So and see the difference. FSI minus Fs, FSI minus Fs, which is equal to 2IF. When this gap is increased, then this IF is also increased. Okay. Now this difference is increasing, IF is increasing. When IF is increases, gain at FSI is decreases. Therefore, a practically preferable method to improve the image reaction ratio is increasing the rho value. Okay. No doubt.